Let's go to the appropriateness of use or when to use Wilcoxon. The Wilcoxon signed rank test is a non-parametric test for comparing two pair-dependent data sets. It is an alternative to students' paired t-test and is used when one or more of the data sets are not normally distributed, and sometimes when sample size is small. Now, the formula of Wilcoxon is W, which stands for test statistic, is equal to the summation of the sample size, excluding pairs where x1 is equal to x2, multiplied by the sign function, times the corresponding rank pairs from two distributions, then multiplied by rank. To better understand Wilcoxon, here is an example. A study is run to evaluate the effectiveness of an exercise program in reducing systolic blood pressure in patients with prehypertension, defined as systolic blood pressure between 120 to 139 millimeters of mercury, or a diastolic blood pressure between 80 to 89 millimeters of mercury. A total of 15 patients with prehypertension enroll in the study, and their systolic blood pressures are measured. Each patient then participates in an exercise training program where they learn proper techniques and execution of series of exercises. Patients are instructed to do the exercise program 3 times per week for 6 weeks. After 6 weeks, systolic blood pressures are measured again. Here is the data. So in this example, we will use Excel to compute. Step 1. Set up hypothesis and determine level of significance. So our null hypothesis is the median difference is 0. And our alternative is the median difference is not 0. And our level of significance, or the alpha, is 0.05. So step 2. Select the appropriate test statistics. The test statistic of the Wilcoxon signed rank test is W, defined as the smaller of W positive and W negative, which are the sums of the positive and negative ranks, respectively. Step 3 is to set up the decision rule. The critical value of W can be found in the table of critical values. To determine the appropriate critical value from table 7, we need sample size n equals 15 and our two-sided level of significance, which is 0.05. The critical value of this two-sided test with n equals 15 and the alpha, which is 0.05, is 25. And the decision rule is as follows. Reject null hypothesis if W is less than or equal to 25. The fourth step is to compute for test statistics. Now, the first thing we do is to find the difference. To compute the difference between before and after exercise program, subtract the cell value from before to the cell value of after. Copy, paste. Now let's go to the positive value column. This is to indicate whether the difference is positive or negative. So, equals, if the value of the difference is greater than 0, 1. If not, negative 1. Copy, paste. Next is to find the absolute value of the difference. Diri mahibaw-an kung pilay difference regardless kung positive ba or negative ang amount. So, equals absolute of the value of difference. Copy, paste. Next is rank. Rank is simply ranking the value of the absolute. Then equals rank number reference which is the whole set. It is important to put $sign before the letter or end number para dili ma-move inig copy paste. Then 1 kay ascending order man. Copy, paste. Next is the signed rank column. Signed rank column is used to sum up all the positive and negative rank. So, multiply the cell from the rank column to the cell that contains positive and negative value. In this way, all of the positive ranks stay positive and all negative ranks stay negative. So from here, makita na to ang positive sum and negative sum. Positive sum equals sum if range sa signed rank, then criteria is greater than 0 para ma-add tanan ang positive rank. Then, range sa signed rank. Then, negative sum equals sum if, then range sa signed rank, then criteria is negative 0, less than 0 para ma-add tanan ang negative na rank. Next is range sa signed rank. From that, makita na nato ang test statistics. How? Simply to choose the lower value of the two. So, ang lower value na to is ang value sa negative sum, which is 27. Last is the conclusion. The conclusion is we do not reject the null hypothesis because 27 is greater than 25. Therefore, we do not have statistically significant evidence at the alpha 0.05 to show that the median difference in systolic blood pressures is not 0. So guys, we will show you a tutorial video using Wilcoxon signed rank test computed manually.
Hi everybody, this is Eugene O'Loughlin, lecturer in computing at the National College of Ireland, and welcome to my series of short how-to videos. In this video, we're going to learn how to perform a Wilcoxon signed ranks test, and we're going to learn how to do this by hand. So before we start any calculations, let's take a look at some data. Here we have some sample data from Lorenz et al. From 2004, and these are examples here where the measured content in the wood of 13 poplar tree clones growing in a polluted area was taken in August and in November. The figures here represent the concentrations of aluminium in micrograms of aluminium per gram of wood, and these are the figures that are shown here. And we'd like to determine if there's a significant difference between the August and November figures. Now we have one group tested twice in August and November, which means that these are paired data. And normally when we want to see if there's a significant difference between paired sets of data, we might use a student t-test, but we can't use that if one or more of the samples are not normally distributed. And if that's the case, then we use the Wilcoxon signed rank test. So before this video, I've conducted a quick Shapiro-Wilk test on each of the August and November sets of data. At an alpha value at 0.05, I've scored a p-value in August of 0.071, which indicates that the data are normal. But the p-value is less than 0.001 for the November figure, indicating that the November data are not normally distributed. And I think if you look at the data, you can see that particularly the last three values here are very, very high, and that they're skewing the November data. Therefore, it's not normal. We cannot use a t-test, and we must use a non-parametric test, in this case, a signed rank test. So as always, at the beginning of a statistical test, let's set out our null and alternate hypotheses. Our null hypothesis is that the median difference between the pairs of observations is 0, and note that the hypothesis is based on the median. Our alternative hypothesis is that the median difference between pairs of observations is not 0. We're going to conduct our test. We have an alpha value of 0.05, and we've got 13 pairs of data, so we have a value of n of 13, which we are going to need a little bit later on. So to set myself up for doing the calculations, I'm just removing that top sheet, and I'm using the same data, and I've added in 3 extra columns that I'm going to need to use here to calculate the test statistic for this Wilcoxon signed rank test. So the first of these here is I want to note the differences between the November and the August data, which is simply subtracting one value from the other. So 12.7 minus 18.3 is equal to minus 5.6. 11.1 minus 13.3 is minus 2.2, and 15.3 minus 16.5 is minus 1.2. And then the next one, I get my first positive value. There's a difference of 0.1, and then the next one is a difference of 1.0, 2.0, and I'm just going to fill this out. I've previously calculated these values here, the differences between the November and the August data. 7.2, 12.0, and we've got some very big differences down here near the end, particularly the last value, 23.4, so a huge difference here at the end, again emphasizing the abnormality of some of the data here. And then in my next column then, I just need to take the absolute difference, which is simply removing any negative signs that you see in this column here. So the absolute value of minus 5.6 is 5.6. Absolute value of minus 2.2 is 2.2. The absolute value of minus 1.2 is 1.2. And then the absolute value of all the positive values here is the same as they are as far as the differences are concerned. So we've no minus sign here. So we're just going to write all of these out as we see them in our data. So our last absolute value is 23.4. Our next job then is to rank these absolute values. This is why we need the absolute values, because we don't want to rank any negative values, but we want to rank all of them. And we're going to rank them from the smallest to the largest value. So reviewing this absolute difference column here, I note that my smallest value, which gets a rank of 1, is my value of 0.1. My next smallest value is the figure here beside it, 1.0, so I'm going to write that as a rank of number 2. And my third figure is 1.2. So as they are increasing, I'm adding in the ranks. The next highest figure is 2.0. That gets a ranking of 4. The next highest figure is 2.2. Gets a ranking of 5. And then the next highest is 3.1, which gets the ranking of 6. Next highest is up here at the top, 5.6, and that gets the ranking the next highest one here is 5.3. Which is rank number 7, and then the next highest one is 5.6, which gets a rank of number 8. The next highest one then is ranking of 6.3, which is a ranking of 9, and then you can see these are all sequential here at the end, so the last sets of rankings are easy to determine here. So just to recap here for a second, our differences, we are very, very important that we note the sign, because this is a Wilcoxon signed rank test. So we need to know all the positives and we need to know all the negative differences. And then we need to know the ranks of all the positives and the ranks of all the negatives so that we can sum them. So we need to know the rank sum for the T pluses and for the T minuses. So to do that, I'm just going to use a highlighter here. So I need to highlight all of the negative values that are conveniently here at the top, and then select the ranks for each of those there. So these are all the negative values. So the rank sum of the negative ranks here is 8 plus 5 plus 3, which is 16. And then I'm going to do the same for all the positive values. So they're all conveniently here for me. So these are all the positive differences, and these are all the positive ranks. This is going to give me my T plus, all the positive ranks. So when I sum up all these values here, 1, 2, 4, plus 6, plus 7, and so on, I'm going to get a T value here, T plus value of 75. The Wilcoxon assigned rank test statistic is called W. So my W stat, what's the test statistic? Well, it is the smaller of these two values here. So the W stat is 16. Just to check back for a second, if any ranks are the same, so if you get two different absolute differences which are the same, you take an average of the ranks for those 2 or 3 ranks in that case. So now our test statistic has a value of 16. We now need to determine a critical value so that we can compare our test statistic with a critical value to determine if there is a significant difference. So to do that, I'm going to use a critical values of the Wilcoxon assigned rank test table. And to check back here, right back at the beginning of the video, I stated that our alpha value was 0.05, that n was 13, and you can also see that we are doing a two-tailed test here. No direction is specified, so it is a two-tailed test. So from my table, the first column gives me the row I need to use, so n is equal to 13. A two-tailed test and alpha value of 0.05, so go down along here, and we get a critical value of 17 in this case. So let me note that. My W crit is 17. So in this case here, my test statistic is less than my critical value. And that results in here of that we reject the null hypothesis. We reject H0. And be very, very careful with this, because many statistical tests, you only reject when the test statistic is greater than the critical value. But in the Wilcoxon assigned rank test, it's the reverse of that. So we're looking for, if we want to reject the H0, we have to get a test statistic less than the critical value. So here 16 is less than 17, therefore our W stat is less than W crit. We reject H0. So in other words, we are rejecting this statement over here that the median differences between August and November are 0. So we are rejecting that in favor of the alternative hypothesis that the median differences are not 0. And we're doing all this at an alpha value of significance of 0.05. So in conclusion then, we have found a significant difference between the concentrations of aluminium between the August and November data for the poplar tree clones. So that's how you perform a Wilcoxon assigned rank test by hand. I hope you found this video useful. Thank you for your attention.
As we can see, it has the same process, but it's much easier in Excel because there are functions available. We can easily find the difference, the absolute value, and its rank, as well as the positive and negative sums. That's all. Thank you!